Okay, at this point we have a system model, but it's not converged. In other words, it relies on these guesses here for the ethylene glycol temperature, and then the volumetric flow rate of the ethylene glycol and the volumetric flow rate of the two air streams. So what we need to do in this video is actually make the model converge, and there's a bunch of different ways to do that. You could set it up as an optimization problem and minimize some errors and the constraints. Ideally, what we would do is just actually one by one set these iteration variables in order to close up the constraints that we had talked about previously. So I'm going to first of all make sure that this get rid of this iteration variable and make sure that TEG1 matches the value right here that I calculated. I'm going to second of all get rid of this iteration variable, the volumetric flow rate of the ethylene glycol, and make sure that the pressure rise produced by the gear pump right here matches the pressure drop on the ethylene glycol side associated with each of the coils. And here I'm noticing that I did not include actually in the outputs the pressure drop in the ethylene glycol side or the air side. So the first thing I better do, I guess, is go here and add two more outputs. And these will be, let's see, what did I call those pressure drops? Delta P ethylene glycol, so delta P EG, and then I also somewhere must have calculated delta PA, so delta P underscore A. And I got to add that to the outdoor air coil model as well. So that's what I do here. And then back here, I'm going to have to add those two outputs to these calls. So here I'm going to add delta P ethylene glycol, let's call it indoor air coil, and delta P A indoor air coil. And I have to add those also to the outdoor air, which is down here, right there. So this would be outdoor air coil and outdoor air coil. And hopefully it still solves okay, and it does. I probably have some unit problems because these need to be in pascals and pascals and pascals and finally pascals. So no unit problems. Okay, so let's do these one at a time. The best thing to do here is get rid of this. Up here at the top, I'm going to have a $var info for all of my ethylene glycol temperatures, so I can give them bounds and give them guess values. So this is T ethylene glycol 1. Let's see, lower will be, I guess, T outdoors, the lower limit, and upper will be T indoor, and then guess is the average of those two. So T outdoor plus T indoor divided by 2. And just to be safe, I'm going to do that also for T ethylene glycol 2 and T ethylene glycol 3. So that's what I've done here. At this point, if I tried to solve, I'd find that I can't. So I think I'd be one equation short basically. So the thing that I want to do then is set this T ethylene glycol 1 calc, so let's call this constraints for convergence or something like that, and we'll call this T ethylene glycol 1 is equal to T ethylene glycol 1 calc. So I've added equation, right? I took an equation away here, I'm adding equation here, and hopefully if I solve, that's interesting. Why that wouldn't work? Oh, calc. This is calc right here. It's always good to spell variables correctly. Yeah, and there you go. So the ethylene glycol temperature that converges is, let's see, these two of course have to be the same. That's my convergence criteria. And you go in at 0.7, you come out at 12.6, and we're setting the temperature rise across the pump to be 0. We could come back and fix that if we want. And that makes sense given an outdoor air temperature of -6 and an indoor air temperature of 21 degrees Celsius. So my first iteration variable has been removed, and I have now satisfied this first constraint for convergence. So that's good. Probably, as long as I have a good set of variables here, I ought to update my guess values and move on to the next one. So it doesn't probably matter which one, but I'm gonna iterate on the volumetric flow rate of the ethylene glycol. So up here, I'm gonna add another $var info. V dot ethylene glycol has to be between lower of 0 and upper of, I don't know, 1, let's say, meters cubed per second. And the guess can be what the guess is now, which is 0.00009. I don't need units there. And again, if I tried to solve right now, I think I'd find that I'm an equation short. And the equation that I want is that the pressure rise across the gear pump, so delta P pump, this pressure rise right here, has to be exactly balanced by the pressure drop on the ethylene glycol side on the indoor coil and on the outdoor coil. And of course, you might add some pipe bends and things like that in a real system, but let's just do this. Delta P ethylene glycol outdoor coil. So now I hopefully can solve and come to some convergence, and it turns out that this is going to be my ethylene glycol flow rate, and that's the flow rate that balances, this 1.4 kilopascal rise on the outdoor coil, and then there's a 2.3 kilopascal rise on the indoor coil, and that's exactly made up by the 3.8 kilopascal rise on the pump. So you kind of see how this works, and by doing it this way, it's a little less frustrating than I would guarantee you that if you just did this all at once, it's probably not going to converge, so it's definitely a lot less frustrating than that. So let's do the next one. This is the airflow on the indoor air coil. So I'll go up here and say $var info v dot AIC. Lower is 0, upper is, I don't know, 0.05. It's probably too big, and the guess is equal to 0.02. I think I'm going to get rid of these units, because I'm not sure that they really should be there. So I come down here and add another constraint, which is that the delta P that, what is this, is on the indoor air coil. So this is delta P, I called it ICB. This is the fan pressure rise, has to be exactly equal to delta P AIC. This is the indoor air coil pressure drop. And if I solve, you can see that it converges nicely to, where am I at here? This is, maybe I put this into CFM. This is 55 CFM. So I'm almost done. Again, we'll update our gas values. This is the last one I have to converge on, is the outdoor air coil volumetric flow rate. I'll add one more of these. V dot AOC, it's got to be between 0 and 0.05 and 0.02. And these guesses, by the way, this guy, and this guy, and the upper limits, I could actually put in variables for these that are consistent with the upper limit of the flow rate that I can get from my pumps and my fans. Alright, so this last one is delta P, I think this, I called this OCB maybe? OCB has to be equal to delta P AOC. And hopefully this solves, and it does. I'll update my guess values one last time, and it turns out then that 55.1 CFM for the outdoor air coil as well. So my system model now has converged. If I want to look at these results maybe in a little bit more clear way, I could probably put this stuff on a diagram window. So here I'm just going to I guess I'll grab that schematic. I'll go to the diagram window. Let's make it a little bigger here, and I'll just paste that schematic right in here as, I don't know, let's do it as a meta file. So this makes a nice place to put things, right? So maybe I'll put some output variables that include things like T-ethylene glycol 1 right here, and I think I'm going to put it in alternate units like that. So that's this temperature coming into here, and then I'll do T-ethylene glycol 2, which is the same as T-ethylene glycol 3. Again, I think Celsius is probably better, so like that. And then I could also do the same thing with these other parameters. So I'm going to put the indoor air temperature, this is an output, T indoor in alternate units, 21 degrees, and then finally T outdoor. Also in alternate units. So you kind of see how this is a pretty convenient way to look at the outputs of the model if I want to. It makes sense, right? I go into 21, and this ethylene glycol is getting warmed up, and then it comes down here, and this is going in at -6, so this ethylene glycol gets cooled down, and you go around and around like that. I can put other things like powers and stuff like that on here. I could even turn this into a fully functioning graphical user interface if I wanted to, but that's a different video.